Okay, hello and welcome to I think the best session on intergenerational linkages. I didn't see a lot of yesterday's papers because I had to go teach, so this is just the ones I've seen that have been great. So we have four fantastic authors here to present. Our first presenter will be Paul Mohnen, who's a research economist at the Atlanta Fed with research interests in the labor market, aging, and economic mobility. Our second presenter will be Ariell Zimran, who's an assistant professor of economics at Vanderbilt University and a faculty fellow with the National Bureau of Economic Research. And his research interests are in the economic history of internal and international migration, and especially the economic history of the age of mass migration. Our third presenter will be Micah Villarreal, who's a PhD candidate in economics at the University of California, Santa Barbara. And in her research, she seeks to disentangle the historical roots of present-day inequality in the United States. Our final presenter is J.D. Denton-Schneider, who's an assistant professor of economics at Clark University in Massachusetts. His research focuses on human capital, especially health, and the intergenerational transmission of poverty in developing economies, past and present. And J.D. earned his PhD from the University of Michigan in 2022. Presenters will have 13 minutes. I'm going to give you precisely timed warnings about when you're approaching the end and when to stop, and I'll let the presenters acknowledge or dump on their co-authors as they choose. So, over to Paul.
Great. Well, thanks for including our paper on the program. It's great to be here. So this is joint work with Dan Fetter at Dartmouth and Lee Lockwood at UVA. And the standard Fed disclaimer applies. So a lot of research on Social Security focuses on recipients themselves. So how it affects their labor supply or their savings decisions. So in this paper, we're instead going to focus on how Social Security can affect the children of recipients. In particular, we're going to focus on some of the earliest recipients of Social Security who turned 65 in the 1940s and 1950s. And we're interested in how their eligibility or non-eligibility for Social Security, as well as the timing of that eligibility, affected the long-run outcomes of their children. Now, the answer to this question is important because indirect long-run effects on children could potentially have important welfare and distribution implications for Social Security. So, why would there be effects on children? Well, our paper revolves around one key conceptual point, which is that because in practice, a lot of the support that adult children provide to their parents takes the form of in-kind transfers that require physical proximity, so think of things like co-residence or caregiving, then to the extent that Social Security displaces those types of transfers, it may have important indirect effects on children, essentially by relaxing location constraints and allowing them to move to places where they have better job opportunities. So to answer this question, we're going to combine two key ingredients. One is a new source of variation in Social Security eligibility. And the second is a new data set we've assembled linking Social Security death records to the 1930 census. Okay, so Social Security was introduced in 1935 as part of the Social Security Act. And initially, only primary workers were eligible for benefits. But the 1939 amendments introduced benefits for spouses and survivors and essentially transformed Social Security into a family insurance program. So to be eligible for Social Security, you typically had to be 65 and had had sufficient earnings in so-called covered employment for a sufficient number of quarters. Now, the key feature that we're going to exploit in this paper is that originally only about 60% of the workforce was covered by Social Security when it was introduced. And Social Security only became the near universal program it is today as the definition of covered employment was expanded over time. In particular, we're going to focus on the first major expansion in coverage, which are the 1950 amendments. And we're going to focus on a subset of workers covered in 1950. Those are nonprofit workers, state and local government workers, and domestic workers. Because these workers can partly be identified on the basis of their industry, the idea is to compare wage and salary workers who had the same occupation, but worked in different industries and were therefore covered at different times. So the kind of spirit of our empirical strategy is captured in this quote by Arthur Altmeyer, who was one of the architects of Social Security and was advocating for sort of the expansion in coverage. And he essentially noted in the 1940s that these non-covered workers were not that different from their covered counterparts in terms of their skills, their tasks, and their earnings. So the types of jobs that are going to be driving our results are jobs that are found both in the private sector and in the nonprofit sector or state and local government or in domestic households. So a good example are janitors. So if you were a janitor, you worked for a private company, then you'd be covered in 1935. But if you worked for a school, a church, or a hospital, then you would only be covered in 1950. Now, one thing I want to stress is that we're not just going to compare workers covered earlier versus later. We're additionally going to explore the fact that being covered earlier versus later has differential bite across cohorts. So let me give you an example to illustrate sort of how our empirical strategy works. So consider a couple in which the husband's born in 1877 and the wife is born 3 years later in 1880. And suppose they both live their remaining life expectancy upon reaching age 65. Now, in this first couple, the husband, let's say, is a janitor, works for a private company, is covered in 1935. So he would accumulate the 10 quarters of coverage he needs to be eligible for Social Security between 1937 and 1939. Then upon reaching age 65, the couple would start collecting primary benefits. 3 years later, once the wife reaches age 65, they would collect primary and spouse benefits. And there would be a period where the wife outlives the husband and she would collect survivor's benefits. Now consider the same couple, but suppose that the husband is a janitor and works in a school, for example. Assuming he doesn't change jobs and keeps working, he would accumulate the 6 quarters of coverage he needs for eligibility between 1951 and 1952. And then there would be a brief period where the couple would collect primary spouse benefits and then again the survivor's benefits. Now that's all under the assumption that the second couple, the second worker works until his mid-70s. In the more likely scenario where he retires before then the second couple would actually never be eligible for Social Security. So that's the sense in which being covered earlier versus later can make a big difference for these early cohorts. Now shift everything 11 years later and consider the same two couples. In this case, the only difference between these two couples is when they would accrue these quarters of coverage. But they would both be eligible once the husband reaches age 65. And actually, if they had the same earnings, they would even get the same benefits. And that's because under the 1950 amendments, sort of Social Security benefits were based on average monthly earnings after 1950. So it didn't really matter how long you contributed into the system. So that's the sense in which being covered earlier versus later makes little to no difference for these later cohorts. So in practice, what we're going to do is parameterize this variation in Social Security eligibility by mapping occupation, industry, and cohort into the minimum age at which a worker would be eligible for Social Security, assuming continuous employment. So this is plotted here in red for 1950 covered workers and in blue for 1935 covered workers. And sort of coming back to the example, you can see that for the earlier cohorts, there's sort of a big difference in the minimum age of Social Security eligibility, but for later cohorts, there's no difference. So that's going to be the key policy variation in our regression analysis. Okay, so in terms of data, our main analysis relies on a data set we've constructed linking Social Security death records to the 1930 census. So in the 1930 census, we can observe your father's year of birth and his employment information 5 years before Social Security was introduced. In Social Security death records, we can observe the zip code in which children last resided in prior to their death, which we're going to use as a proxy for their long-term socioeconomic status. So the idea here is that if you die in a high income or high house price zip code, that sort of says something about how well you did over your lifetime. Now, instead of linking these records directly, we're first going to merge Social Security death records to Social Security application records and link those records to the 1930 census. And the reason is that Social Security application records additionally contain information on parent names, which is going to allow us to do two things. It's going to allow us to link children and their parents as families to households in the 1930 census, which is going to sort of increase the quality and number of links we're able to make. And it's also going to allow us to link women because women typically appear under their birth name in the earlier census, but under their married name in death records. And we make these links using the LifeM supervised machine learning approach. Now, one thing to keep in mind is that the Social Security records that we have access to only contain a subset of our population of interest, and particularly should think of these records as sort of containing the near universe of children who died between 1988 and 2007. So at the end of it all, after imposing some sample restrictions, we're left with around 500,000 sons and $500,000. Okay, so our main regression specification is going to regress average outcomes among children on the father's predicted age, minimum age of Social Security eligibility based on his employment information 1930, which I showed you a couple slides ago. So the main coefficient of interest here is beta, and minus beta captures the impact of fathers being predicted to be eligible 1 year sooner on their children's average outcomes. So to implement the spirit of our empirical strategy, we're going to net out level differences by father birth cohort and level differences by Social Security coverage years. And we're additionally going to narrow these comparisons to be within occupation by interacting the birth cohort fixed effects with three-digit occupation fixed effects. So to support the validity of our research design, in the paper we do 3 things, which I'm just going to briefly describe here. So one thing is that, you might think that, well, these workers that are covered later, they can just switch occupations and become eligible sooner. So in the paper, we show using a separate data set linking Social Security claims records to the 1930 census that there is a sort of first stage. So our Social Security eligibility variation based on 1930 employment information is predictive of actual future claiming patterns. Second, we do a placebo check and show that our Social Security eligibility variation is not predictive of pre-existing family characteristics in 1930. And lastly, we run a selection test and show that our variation is not predictive of being included in the link sample or not. Okay, so this graph shows our main results. It plots the estimated betas from that regression. And here the outcomes are the average neighborhood quality of children, where we rank neighborhoods according to mean income in the left panel, median house price in the middle panel, and some sort of neighborhood quality index in the right panel. So you can see from the red bars that if you pool sons and daughters together, there's sort of no statistically significant effects. But this masks sort of heterogeneity across sons and daughters. So if you look at sons, the green bars, the negative coefficients imply that fathers being eligible sooner has a positive effect on their the rank of their zip at death. In terms of magnitude, sort of a 10-year difference in predicted eligibility translates into an improvement in the rank of their zip code at death by around 2 percentiles. In contrast, for daughters, the blue bars, you don't see any significant effects. Now, in the paper, we complement these results with some survey evidence where we have direct measures of sons' earnings in adulthood, and we find some positive effects sort of consistent with these zip results. And you might wonder, why are there effects on sons but not daughters? So our kind of working hypothesis is that sons and daughters differed in terms of the types of support that they provide to their parents. In particular, there's some suggestive evidence that daughters tend to provide more caregiving than sons, for which Social Security benefits may have been a poor substitute because the markets for those services wasn't as developed back then as it is today. Okay, so in the paper, one thing we do is we sort of do some back of the envelope calculations to sort of establish that the lifetime financial gains to all children were large relative to the benefits that their parents received. Now, I'm not going to go through the details of this calculation, but intuitively, the gains were large for 2 reasons. One, even modest per period gains can add up to a lot over long periods of time. And 2, families had multiple children. Instead, in this last slide, I'm going to focus more on the sort of mechanism behind these long-term gains. So one natural explanation is that parents simply pass down some of these benefits to their children. Now, that might be part of the story, but there are 2 reasons why it's unlikely to be the sort of explain all of this. Qualitatively, it's unclear why downstream monetary transfers would lead to labor market gains or differential effects by gender. The reasons that, income effects will tend to induce you to work less, not more. And there's some sense that these sort of downstream monetary transfers tend to be gender neutral. Second, quantitatively, it's unlikely to account for more than a small share of the total gains. And that's because you have to take into account that first, the gains were large relative to benefits, and these benefits get split across multiple children. Instead, the data seems to suggest that migration to better matched labor markets was a key driver behind these long-term gains. So the main piece of evidence to support this story is that we find that sons whose fathers were more exposed to Social Security were more likely to die outside of their parents' last known county or commuting zone of residence. And so That's sort of consistent with this labor market gains story. And it's also consistent with these differential effects by gender because we don't find any migration effects for daughters. And lastly, it can plausibly account for a large share of the total gains because the literature tends to suggest that the returns to internal migration can be fairly large. So to conclude, in this paper, we provide new evidence on the long-run intergenerational effects of Social Security. We find that sons of early recipients died in better neighborhoods and they had higher earnings in adulthood. And we find some suggestive evidence that migration to better matched labor markets was sort of a key channel behind these long-term gains, consistent with this notion of the displacement of a location-constrained family support. So the bottom line is that, so if you're interested in the overall welfare and distribution implications of Social Security, it's important to take into account these long-run indirect effects on children. Thank you.
Hello, thanks everybody for being here. Thanks so much to the organizers for including this paper on the program. It's really wonderful to be here and to get a chance to thank in person the folks whose work has been so important in underlying so much of my research agenda, so thank you. Today I'm presenting a paper titled Using Discrepancies to Correct for False Matches in Historical Data. This is a paper in which unfortunately you're going to learn nothing useful about the real world, unlike all the other papers that you've seen here today and yesterday. But hopefully this will expose you to a tool that can be useful in helping you to learn about the real world. But I'm going to run some regressions here that are probably not very interesting, but they're for illustration purposes only. And so this is joint work with my colleague at Vanderbilt, Yuya Sasaki, who is an econometrician by training and who's responsible for all the kind of infrastructure underneath the stuff that I'm going to show you. So as we've learned at this conference, linked data in general, and in particular the analysis of linked census data, is really increasingly important across many disciplines and in many disciplines of social science history, especially economic history. But a really fundamental issue here is false matches, right? We know that we're not going to get all the matches right. Now, in some cases, this will be more of a problem than in others, but two issues where it really is a very big deal is, number one, if you want to study internal migration in the United States, so you can only do this using linked data before 1940, because that was the first year that the Census Bureau asked about prior place of residence. But the problem is that if you make a false link and you're looking at county migration with a probability close to 1, that false match is going to look like somebody moved when in fact they may not have. Similarly, if you're interested in intergenerational mobility, say a rank-rank regression between fathers and sons' occupational status, or occupational income score percentile, you're going to mechanically understate that correlation because many of the people who you're linking to one another aren't actually connected in reality, and so there's going to be no correlation between them. You're going to wind up overstating the degree of mobility. So what do people usually do? Well, usually what I've seen done in the literature, and this is something I've done in much of my work, is to say, well, okay, what we're going to do is we're going to do our analysis with our linked data set, and then what we're going to do is we're going to take that data set and somehow make the match quality better, right? We're going to make the linkage criteria stricter. We're going to use the intersection of different methods of matching, and this is going to reduce our rate of false positives, and we're going to show you that our estimates don't change that much, right? You can think of this as being really similar to what we do when we make like a coefficient stability argument when we run a regression, right? I'm going to run a regression, and I'm going to include a bunch of controls, and the fact that the coefficient estimate doesn't change a ton or doesn't become insignificant when I add these controls, that should tell you that you shouldn't think that omitted variable bias is all that important, right? So that's informal, but there's a something underlying it. And so what I'm going to talk about today here is basically taking this kind of idea and making this into a formal approach to address the bias coming from false matches and linking. This is going to build on kind of two major bodies. Well, I'm not going to call my own work a major body of work, but one major body of work in econometrics, the dyadic data literature, which is a very, very new, my understanding, a very new field in econometrics, and also some work that I've done on internal migration, right? So I have papers on the internal migration of immigrants in the United States during the age of mass migration, and on the internal migration patterns of white men, in which I really had to take very seriously this issue of false matches. I wanted to estimate migration rates. And so I had to deal with this false match issue. And I had an idea of like, what can I do kind of informally to deal with this issue? And then I went to my colleague Yuya and said, let's turn this into something formal. So the idea is to say, well, there's some characteristics that maybe we don't use in linking, or maybe we do use in linking, but we don't force to match. If we take a linked sample and we see that some characteristic that isn't supposed to change has changed over time, like the father's birthplace, for example, this can give us some way of estimating the rate of false match. If we then can determine, okay, what kind of is the bias that comes from a false match, right? In what direction is a false match driving my estimates? Then we can basically back out the corrected estimate, but also very importantly, we actually can do proper inference because of this dyadic data literature. We actually can compute standard errors here. Right? So what I'll do is just, I'm not gonna show you any econometrics here. I'll illustrate for you the intuition, the idea here of what we're doing. I'll show some simulations just to show you kind of, hey, this method works. And then I'll just give some very, very simple empirical examples to kind of show you like, how this thing works in practice. So the intuition here is very simple. It's based on the law of total probability, right? So the idea here is, theta is some quantity that we're interested in. It's a migration rate, or it's some, component of our regression estimator, like x prime x or x prime y, right? Something very simple. So the value that we observe, this e theta, is a mixture of two things. It's a mixture of the theta that comes from the true matches, and it's the theta that comes from the false matches, right? So the observed migration rate, say, among the false matches, so close to 1, and that among the true matches. And the mixture is governed by the rate of false match. So if you just rearrange this, what you can get is, this thing that we're interested in, right? The theta, but just the one from the true matches, is a function of this here. So it's a function of e theta, right? So that's just the value that we observe in our linked data set. It's a function of the rate of false match, and it's a function of the theta that we get from the false matches. So in order to actually put this thing into practice, what we need to do is, number one, get an estimate of the rate of false match, and number two, figure out what are false matches doing to the thing we're interested in. So the false matches, the way we get at this is to think about, okay, where are we seeing discrepancies in non-linkage variables? So for example, you can say, okay, one characteristic that often isn't used in linkage is parents' birthplaces, right? So if I link somebody from census 1900 to 1930, in one census it says their parents were born in Italy, in the next census it says their parents were born in New York, right? In principle, that should never happen. I know it does in reality and sometimes, and we'll deal with that. In principle, it should never happen, and so this can give us a sense of, what is the rate of false match. And the nice thing about this method is you can define this really depending on your context. You can say, I'm going to define a false match as occurring when any variable mismatches, or when all of a set of variables mismatch, right? You can do this kind of however you like. Now, again, this again just comes from the law of total probability, right? The probability of the false match is the probability that you observe a discrepancy in the data set minus the probability that you get a discrepancy in the case of a true match, right? And that's going to be an important thing, divided by the probability that you get a discrepancy in the case of a false match, right? So how likely are you to observe, if you make a link between two random people, how likely are their parents' birthplaces to disagree, right? Now, if you're willing to assume that these discrepancies shouldn't occur in the case of a true match, this becomes a very simple expression, right? But you don't have to, right? You can, and I'll talk a little bit about where you might kind of bring in this probability of a discrepancy, right? The probability that in reality, like if I make a true match, that maybe even then, like parents' birthplaces might disagree. And the nice thing is you also you can allow the matching to be what we call either confounded or unconfounded. So unconfounded is everybody has the same probability of being matched falsely, but you also can allow the probability of a false match to vary according to population characteristics as long as those are discrete. So for example, I can say, immigrants and natives might have a different probability of being falsely matched, or people with high occupational status and low occupational status might have a difference, and the method can accommodate that very easily. So then the other issue that we have is where is the false match driving our estimates, right? How is it affecting our estimate of the quantity of interest, and how is it going to give us the, how do we know what the probability of a discrepancy that arises from that is? And this is pretty simple. What it requires you to do is just to consider all possible pairs of matches. So take everybody in census 1, everybody in census 2, right? Make all the pairs of possible links, right? And you can block however you want to block, and basically just take the average from all the links that you get, and that is essentially the average, the value that's coming out, right? It's essentially if I mismatch you, I match you to some random person, and that allows me to just estimate, okay, if migrate, what's the probability that if I match you to some random person, you look like you migrate? Very close to 1. What's the rank coefficient that would come if I matched you to some random person, right? Higher than the truth, probably, right? What's the probability that your parents' birthplaces disagree if I make you a random match, conditional on the birthplace which is used in matching? So that's really the whole, the estimation really is not much more than I've said there. The actual like going and computing the quantity of interest. The problem is that the inference, the computation of standard errors is based on these new results for dyadic data. Yuya tells me that if I'd asked him about this project 3 years ago, he wouldn't have been able to do anything. But now like the standard errors take like pages and pages and pages to write down. And the problem is that because we're looking at all these possible pairs of matches, the order of the problem is on the scale of the product of the two census observation numbers, right? So we're talking here about billions of observations. The nice thing is if you're willing to make kind of certain assumptions like, I'm going to look at migration, which limits the space of outcomes, or I'm going to regress an outcome from census 2 on an X variable from census 1, right? You can really simplify this down as long as you're, I've done a lot of really nasty algebra, which allows you to then simplify it down, and the estimate becomes tractable. All right, so let's look at some simulations. So for migration here, so I'm going to have 2 censuses here, each with a size of 1,000, 20 locations that people can live in. In the true probability of migration is 25%. I'll link 25% of people, and 25% of those links will be incorrect. We'll have some discrepancy characteristic, think of it as like a parent's birthplace with 5 categories, and I'll run 2,500 replications. So this is just the results of estimating the false match rate. So you can see that the estimates really cluster around the true value, which is nice. If we go and estimate the migration rate, we can see that if we do this incorrectly, we're going to wind up overstating the rate of migration, right? So these uncorrected estimates really sit much above the truth. The corrected estimates do a good job. And this is basically showing that we can do a good job of actually estimating the standard errors, right? So the standard deviation of the estimates is well approximated by the actual standard error that we compute with our measurement, with our formula. We can do something similar. Let's look at a regression across 2 censuses. I'll just show you that we do a good job, right? Think of this as an intergenerational rank regression. I just want to get into the examples. So looking at some examples. So again, migration. So what I've done is I've linked the 1910 to 1930 censuses with the ABE conservative exact matches. We'll look at county level migration, and if we just make the link and look at how many people move, we get about 45%. We'll block on birthplace and birth year. This requires us to consider about 151 billion pairs of observations. I don't know of a computer that I have access to that can do that, but because of the simplification, this can run on my desktop in a few minutes. So what do we get? Well, if we define a discrepancy as the father's birthplace not matching, we estimate a false match, or the mother's, we estimate a false match rate about 40%, and estimate a migration rate of only about 15 to 20%. Pretty, it seems like a high false match rate. We can say, oh, okay, the false match is going to be if both of these things disagree, that reduces it still and gives us a lower estimated estimated migration rate. But this still doesn't square with like what I've found in my work on the subject. What are the migration rates? What we can do though is we can say, let's allow a certain kind of base discrepancy rate. What's the probability that in a true match, somebody's parents' birthplace disagree with one another? So you can get at this in many ways depending on your context. What I've done here is I've gone to the strictest possible matches I could get. I took matches that I've made, the 2 different ways that ABE match, looked at the intersection of those matches and took the discrepancy rate from that as the base. But you can do this if you use machine learning, like from your training data. If you, I talked to Joe Ferry yesterday, which of course 2 minutes with him is more valuable, I think, than time with most other people. And he suggested that you can go to the 1880 census and look at the double transcription or double enumeration of St. Louis, right? So same people enumerated at different times, how much do their characteristics change, right? So depending on your context, you can feed in a base rate. And then what we come out with is a false match rate 1910 to 1930, about 4%. This is the native-born white population, an estimated migration rate of about 40% over 20 years, which is very, very close to the numbers I got in my own project, my earlier project, which is based on a completely different set of discrepancies. It's based on comparing interstate migration rates based on linkage and children's birthplaces. This is just to show that matters a lot, the base discrepancy rate that you say you said it changes a lot, the estimated migration rates, which is not surprising. We can also go and do something like a rank regression. So look at the 1900, 1930 censuses, same kind of linkage, take kids in 1900, adults in 1930, and just take the Oxscore percentile ranks of the father and the son and regress the sons on the fathers, right? If you don't correct, you get a rank coefficient about 0.33. Again, dealing with a huge number of pairs of observations, but this will still run in just a few minutes. And if we go to just like this corrected, this discrepancy based on the intersection of matches allow an 8% discrepancy rate, we wind up with an estimated false match rate of about 3%, which squares with what other people have found in this context, and an estimated rank coefficient of about 0.33. So substantially lower than the so not very different, I should say, than what we actually see from linkage. And so what this is telling us is that in this context, right, yes, we may be getting false matches at a some relatively high rate, but it doesn't actually make much of a difference to our estimates, because I guess what it means is that the rank coefficient that comes out of just a random permutation is not very different from what we get in the true links. All right, so what we've done here is to develop and introduce a method that corrects for false matches in linkage with the appropriate inference, crucially. And that's based on these discrepancies in the non-linkage characteristics, which we suggest that really anybody who's using linked data can use, at least as a robustness check, right? It's not going to be able to necessarily do all the things you want to do, but you can show us maybe that, hey, it doesn't really matter for my estimate what the linkage false match rate is, and so you shouldn't worry about it too much. Now, the big question, of course, that you might be thinking is, well, why don't we just use these characteristics and make our links better? Now, you can, but in reality, there's a few things. The fact is that in many cases, the links that you get don't use it, and so you can use that information. There's also, like the linkages that use this additional information, like MLP, I believe, correct me if I'm wrong, or like the Abramitsky, Busan, and Erickson extra information matches. They take the information into account, but they don't force it to match, right? And so you essentially, what you can do is you can say, now I'm going to look at like really, really good matches and back out some information from those, and then use that information. So what are we doing next? We're still working on this. The big thing, really the big thing is we are hoping to get this Stata package out there, but we still have some of the underlying hardware or machinery to work out before it's ready. We need to allow weights to deal with selection into linking. We need to kind of allow empirical applications of the confounded matching, because this many billions of pairs has to be dealt with. But we hope to have something soon. So stay tuned. Thank you so much, and feel free to reach out with any questions.
Great. Thanks, everyone. Today I'm going to be talking to you about black gold, the effect of wealth on descendants of the enslaved. So, as many of us may know, the black-white wealth gap is one of the largest and most persistent gaps in the U.S. today. The wealth of Black Americans is less than 20% of the wealth of white Americans. Recent research in economics argues that the majority of this gap can be traced all the way back to the initial difference in wealth at the fall of slavery in 1865. If that is the case, we might expect that short-term wealth shocks to descendants of the enslaved may have had the potential to spur a virtuous cycle of generational wealth accumulation. On the other hand, we can all think of many reasons why wealth shocks to descendants of the enslaved may have dissipated relatively quickly, even within a generation. So my big question in this project is whether short-term wealth shocks have the potential to narrow racial wealth disparities in the long term. In order to answer that question, I leveraged quasi-random oil discoveries on Black-owned land in the early 1900s to study how large positive wealth shocks may have affected Black economic progress in the short and long term. So for this project, as of now, I've constructed 3 sets of novel microdata. The first is data on the nearly 7,000 Black landowners who lived in the greater Tulsa area during the early 1900s. Second, I construct geodata on the 1 million acres, more than 1 million acres of land owned by these people. And third, I also have the universe of oil-producing wells in Oklahoma, their location and their dates of completion. Okay, so an overview of my results. I do find that positive well shocks do seem to have positive effects on the first generation treated. So within the first 2 decades following the oil discovery, freedmen who find oil, if they are children, they go to school at higher rates. If they are adults, they have higher status occupations. They own their home at higher rates. And then by 1940, I'm actually able to show that they report higher rates of high school graduation and even college going. I'll just go quickly through this during the interest of time. In the economics literature, we often find that the effect of wealth shocks is pretty transient and modest. and that even if it's demonstrated in the first generation, it really doesn't last very long within generations. And there's a large narrative literature of people who are skeptical that any sort of land or wealth transfer policy could have had really any impact on equalizing emancipated people. And then lastly, I'll just note here that in developing countries, there's a really huge conversation about the existence of poverty traps. And so the idea is that one-time policies actually can have permanent effects if they are large enough to lift people out of the poverty trap. Okay. So now I'm going to go through my history. There's a lot of it, so buckle up. So we're going to start before 1930 in present-day Georgia and Alabama. There was a tribe called the Creek Indian tribe, and they practiced agriculture, and in an attempt to assimilate into the white population, some of them did own slaves. And so in 1830, they were forcibly moved west to present-day Oklahoma during the Trail of Tears, and they brought their enslaved peoples with them. In 1865, as we know, slavery was ended by the Civil War, and many formerly enslaved people, known as freedmen, remained in the Creek Nation and became Creek citizens. In 1898, the Curtis Act ruled that the Creek Nation must undergo something called allotment. Now, what is allotment? This was a federal policy that divided communal tribal land into privately owned parcels. And so in the case of the Creek, every Creek citizen was entitled to an allotment of 160 acres. So that was regardless of age, gender, and important for me, former enslavement status. And so in case you don't know acres, the Minneapolis Sculpture Garden is 11 acres. So that's about, an allotment is about 14 Minneapolis Sculpture Gardens large. Okay, so I have some photos here to illustrate. On the left there, that is the Creek Nation. It's probably about 10% of the size of Oklahoma. And on the right, I have a 6-mile by 6-mile map of a piece of the Creek Nation. And that township is broken up into even smaller pieces till we get to the size of an allotment. And so you can't see from your seats, but each of those pieces has a name written on it of the person who was allotted that land. Okay, so timeline. In 1901, the first oil discovery in Tulsa was located on an allotment of a Creek native named Sue A. Bland. In 1905, the first gusher officially kicked off the Tulsa oil boom, and this was also located on an allotment of a Creek native named Ida Glenn. And that's a picture of a gusher, so in case you didn't recognize. In 1907, Oklahoma became a state, and in 1912, the city of Tulsa proclaimed itself the oil capital of the world. Okay, so you can probably see where this is going. I have here a picture of a little 10-year-old girl named Sarah Rector. She kind of overnight became known as the richest Black girl in the world when a producing oil well was drilled on her land. So I have a quote from 1914 that Indians, white men, and Black men are being made into millionaires almost overnight in Oklahoma these days. The money is pouring in a golden stream into the hands of people who a few years ago were as poor as the small rodent in the sanctuary. Okay, so my data. The first thing I did was I built a database of freedmen allottees and their land allotments for the whole Creek Nation. So there's 6,836 of these freedmen people. Second, I built a database of every well completed in the Creek Nation between 1900 and 1934. And this came from like a regulatory commission of utilities in Oklahoma called the Oklahoma Corporation Commission. So these are like geologists. Okay, and the third thing I did was I assigned treatment by linking every oil well to the allotment data in order to observe whether each freedman allottee was assigned treatment, they got oil, or assigned control, they did not get oil. Okay, so my allotment data, out of the box, I know some limited microdata about all of them, but for all the other covariates, I have to link them to the full count censuses. And so as Ariell alluded to, I have to kind of go through different methods and design my own linking strategy based on some information that I have, based on some links other people have made, like the census tree in particular. But the important thing is that the linking rates that I achieve are identical between treated and untreated people. Okay. So balance, I'll go through this quickly. The treatment and control units were similar on census observables prior to the realization of whether they are treatment or control. And so they're the same on urban status, home ownership, rates of marriage, income and work characteristics, and at school attendance, as well as literacy. So this is 1910. Okay, so some of my results. I don't do a longitudinal analysis yet. In order to examine cross-sections and interpret them as causal, I rely on the assumption that distribution of oil is orthogonal to underlying characteristics. And so the following figures that I display are just simple point estimates of linear regressions, and my standard errors are robust to heteroscedasticity. The headline is that treated folks do seem to be doing better in 1920, 1930. In 1940, the results are still in progress. They're a little bit imprecise right now, but I'm of course looking at the direct effects of those treated and also their children by that point, who many of whom are adults. Okay, so in 1920, we see that people who receive treatment are disproportionately in white-collar jobs. And this was not the case in 1910. And so I split up the AUK 1950 variable from IPUMS into these three categories that are used sometimes in the literature: white-collar, blue-collar, and farming. And we can see that treated folks are in white-collar occupations at a 9 percentage point higher rate. And that is the same in 1930. Actually, it's larger in 1930. They are in white-collar occupations at a rate of 12 percentage points higher. And so you can see that that's coming almost directly from farming down there, which is now 16 percentage points less likely. So that's kind of neat. But unfortunately, by 1940, I don't see the effect anymore. And my gut feeling is that I just need to keep linking and figure out if that effect persists. But it's also possible, and I'm open to the idea that maybe these effects did fade in 30 years. And so educational outcomes, which we're all interested in as demography people, in 1940, people who receive treatment are more likely to have completed second grade, and they are also more likely to have completed high school and college, but only at the like 5 or 10% level, which is why it's why the confidence intervals go over 0 there. So I thought that was pretty neat, especially because the rate of college going for the Black population at this time in 1940 was something like 1%. So 6 percentage points more than that is like, it's pretty good. Okay, so possible mechanisms, I'm thinking about geography. So in 1920 and 1930, I do see that people who received oil are more likely to have moved to an urban enumeration districts. And so I'm not sure if the education and the occupation effects are simply mechanical because there are more opportunities for those things in those areas. But if they are, then it still seems important to me that loosening the budget constraint by getting this money allowed them to go to places where their work was better, but better paid, kind of similar to what Paul found. And then the other thing, which goes hand in hand, is that the allottees who are themselves children in 1920 are going to school at a 14 percentage point higher rate in 1920 than the ones not going to school. And so again, that might be kind of another measurement of them moving to cities, but something that probably led to them going to college at higher rates and graduating high school at higher rates. Okay, so what am I doing now? I'm always linking all the time. I have like okay rates. I matched 64% to 1910, but I'm really trying to get to 1940 so I can talk about income and occupation more. And of course, I really care about intergenerational effects, and so a lot of my time is spent linking the adult allottees, the adult children of allottees to 1940 to examine those impacts. And lastly, I have a huge undertaking where I'm digitizing the lease agreements between these oil companies and the freedmen who got royalties, so that I can better quantify the size of and duration of oil royalties to individuals. Yeah. Okay, so in conclusion, I argue that oil discoveries in 1900s Oklahoma was quasi-random and that its impacts can be examined through the lens of an unconditional cash transfer, randomly distributed to descendants of the enslaved. I do find suggestive evidence that in the decades following treatment, treated Creek freedmen look different on a number of different outcomes than control Creek freedmen. And lastly, this context will be central to a number of interesting questions and papers and will motivate a fruitful research agenda. Thank you.
Thank you, everyone, so much for staying through to the end, the bitter enders. I really appreciate that. Thank you also to the organizers for including this paper on the program. This is joint work with my colleague Jenny Mayo, who's at the University of Missouri. So we've heard a bit, just in the session about cash transfers, sort of these welfare programs. And our motivating question in this project is, what are the effects of these cash transfers, specifically to low-income individuals across their lives, and then also into their descendants' lives as well. So we've got some recent work on the impact of food stamps, just given the timing of when the food stamp program was rolled out in the 1960s, and data availability. We can understand the effects on adults who were in the households of beneficiaries when they were children. And then I'm also a development economist, and so there's been some very nice randomized controlled trials of basic incomes or cash transfers. And I think these authors have just put out a 7-year follow-up. So, that's very impressive, but still not kind of getting to our question of interest here. So what Jenny and I are going to do is use what we believe, don't quote me on this, but what we believe is the world's first cash transfer program, which was in England and Wales, beginning in the basically 1600 and then ended in 1834, or significantly modified in 1834. So there was wide geographic heterogeneity in England and Wales at this time, in the generosity of cash transfers to poor individuals. These were called, at the time, called poor relief. And so we're going to exploit the fact that in 1834, the new poor law ended this heterogeneity in cash transfers and use that to identify the effects specifically of, I guess, the sort of the mirror image of this question: what is the effect of ending cash transfers on outcomes in one's own life, in one's father's life, or grandfather's life on the outcomes of interest? So it's a short presentation, so I'm not going to go through the summary. I'll just get right into the history. So around 1600, the old or Elizabethan poor laws were put into effect. These gave parishes, so sorry, parishes are not religious parishes necessarily. They are sort of the smallest, like municipalities, basically. It's just the name for the smallest administrative unit. So these parishes had the responsibility to care for those who cannot support themselves. And they were allowed to pass taxes on property or land to raise revenue. And so in some places, these were quite high. They reached almost 40%. And generally speaking, this would be this poor relief would be provided as weekly stipends or subsidies or in-kind things like clothing, and also in general, they were provided to, who we think of as the indigent, those who really couldn't provide for themselves. However, some parishes, because there weren't really any restrictions, gave assistance to able-bodied individuals when their earnings fell below a certain subsistence level, not like a hard cutoff, just sort of, by their definitions. So this system, continues on into the 17 and 1800s, but it really starts to explode for a number of reasons after 1750. I'm not going to go through those here, but I'm happy to chat and discuss the history afterward. So it doubles as a share of GDP. It was initially 1% of GDP that was being transferred to low-income individuals, goes up to 2% around 1830. But again, as there's wide geographic heterogeneity by parish, in some places these transfers are making up 20% of household budgets. In others, they're less than 5%. So why this program ends is basically the rise of political economy. Malthus was also writing about this. I have Ricardo's a passage from his book up here. But basically, this system was getting very expensive, and people started to think, okay, well, we're going to start spending, infinite amounts of money on this. We're going to bankrupt the country. We have to stop. We've got to get this program under control. So what happens in 1834 is that the new poor law basically, makes able-bodied people no longer eligible for poor relief. And just to see the kind of the time series of what's going on here, social spending as a share of GDP in England and Wales, immediately following the passage of the poor law, returns down to 1% of GDP. About 15% of the population was receiving poor relief prior to 1834. It drops to about 10% with the exception of 1848, which has got famine and revolution and lots of weird things going on. But it really, stays around 10% and below for the rest of the 19th century. And what this looks like, in part is, your classic Oliver Twist. This is Dickens published it in part as a criticism of the new poor law. He also focused more on the urban rather than the rural effects. But, that's kind of the framework you should be thinking about. Okay, so what Jenny and I are going to do is basically do a difference in difference across several generations, basically comparing, if you were interested in childhood exposure. So if you were a child, before the poor law was passed, we think of you as sort of being our control group. If you were a child after the poor law was passed, we think you as being treated or exposed. And then we're going to compare across high versus low decline counties. So if you were in a county where your family was losing a larger amount of its household budget as a result of the poor law, you'd be treated. If you were in a low decline county, you'd be in the control group. So we're aggregating up to the county level. We're in the process of digitizing and collecting and digitizing the parish level data. Counties are like US states, basically. There's actually 50 of them in England and Wales. So we're splitting here at the median. The counties in blue and green, those are our low decline counties. In red and yellow, those are the high decline counties. So you can see they're very much concentrated in the southeast of England, which is a heavy wheat farming area. So there is some hypothesized connection between the number of people who are working on wheat farms and their need for poor relief. So we are using the full count 1861 census of England and Wales from IPUMS. The econometric specification is up here. It does, what I just described. Let me just also say we're including a term here that allows for specific trends in outcomes, separate trends in England and Wales. So we're trying to do something about the fact that we're looking at over a very broad geographic area. But that's what I had just described in words is what's going on in this equation. So the first thing we look at is if an adult in 1861 is in a low-skilled job, where we're defining low-skilled as using the International Labor Organization's classification of various skill contents of jobs. And so you do see a negative effect, or I'm sorry, we're looking, I'm flipping that around. We're looking at high skilled jobs. So a negative effect means you are more likely to be in a low skilled job if you were more exposed as a child to declines in poor relief. It looks like a small effect because of the scale we're using. We do the scale because when we look at women, the confidence intervals are much wider. So just to keep things kind of constant, the effect size is larger, although it's more imprecise. So we're seeing fewer men and fewer women in high skilled jobs as adults. The next thing we'll do is in 1861, we'll look within the households of those individuals who were exposed as children, use the same basic strategy. The difference is we are now attaching their father's treatment versus control status to those children. But it's, again, the same econometric specification. Now that we have variation in age, because they may have a child who's 5 or a child who's 15, we want to control for that. We're going to add in controls for age as well. So we can look at whether a child is listed in the census as a, quote, scholar, unquote. I would love to be listed in the census as a scholar, but anyway, so you did have 3-year-olds being listed as a scholar. I imagine that's a preschool scholar, but still a scholar. So if your father was more exposed as a child, you as a son are less likely to be in school in 1861, and as a daughter as well, roughly the same effect size. So it's about a 2% effect, 2 percentage point, roughly 3 to 4% effect on school attendance. Okay, everything I've just showed you thus far, I feel like hopefully everyone is on board with it. We're going to do some linking, and we may lose a few of you here, but we're doing some stuff to address this. So I just want to say that this is kind of preliminary results for the linked sample. So we are taking those sons in 1861, trying to link them to the 1901 census, also from IPUMS, using the Abramitsky, Bustan, and Erickson algorithm. In the IPUMS data, we have surname, parish of birth, and year of birth. So one very nice thing about the England and Wales data is, unlike the US data where you only have state, here you have parish. There's about 15,000 parishes in England and Wales. So it's, in theory, one could get very great match rates. The issue is we only have surname in the IPUMS data. So we've finally gotten access to the UK data service gave us first names. And so our match rates have gone up to 15, 20, 25%. What I'm showing you here are with these match rates of about 2%, which is not great, but we can do some things to sort of adjust for the fact that we have quite low match rates. I'll just skip over that. So we can look at whether a son, so now that the second generation in 1901, whether you're in a high skilled job, and things are quite noisy, unfortunately. We can also look at sort of thinking about a quantity quality trade-off. So if you are poorer, you're going to be more likely to have more children. We can look at an indicator for whether you have a below median number of children. So we think of, if you are having fewer children, you are more likely to be, sort of in a high skilled, potentially high skill or higher income job. So we do see some noisy evidence of, this quantity quality trade-off among more exposed children of more exposed adults. Sorry, no, the second generation. So the adult children of children who are exposed as adults. That's probably more confusing. But anyway, the second generation. And so this is a point in English and Welsh history where human capital starts to matter more. So we do think that this is, we would expect to see this kind of result. Unfortunately, it's not super clear. So we're also going to look within those households, the same kind of thing, and find those children, their children, so the grandsons of those who are initially exposed, do the same strategy, attaching their grandfather's treatment status, and see what's going on here. So they don't ask about schooling in the 1901 census, but they do ask if you are employed. And so we are taking the fact, if a child is not employed between ages 11 to 15, we think they're in school. So not being employed here is a positive outcome. So we're getting less non-employment of children, so less children in school. Sorry, these are grandsons. And this is quite a precise and clear effect. For granddaughters, it's much noisier. But we still see the same pattern, basically, that the grandsons and the granddaughters of those who are exposed as children are less likely to be in school in 1901. So let me just wrap up by saying, now that we have the first names, our match rates have improved. I'll just kind of preview those results. We've gotten basically the same results, more precision, which has been very nice. We think we're going to get a lot more precision when we can get data at the level of 15,000 parishes rather than just 50 county. But we think that our main contribution here is to show that if you're just thinking about the immediate effects of a program on the adult beneficiaries, the cost benefit analysis might say, well, we should cut this. These people aren't getting any richer. But we need to be thinking about these multi-generational effects when we're doing the cost benefit analysis of these programs, so we don't end up making a suboptimal decision that has negative impacts on generations to come. So thank you very much.